This video is about a particular type of vector field called a conservative vector field. We will define conservative vector fields. We'll discuss a test for conservative fields in R2 and a test for conservative fields in R3. And I'll show you how to find the potential function for a conservative field F. So here's the definition. We say that a vector field F is conservative if there exists a differentiable function f such that the gradient of f is equal to that capital F, the vector field f. In that case, the scalar function f is called the potential function for the field f. If you're wondering where all of this terminology comes from, you see potential, you see conservative. If it reminds you of physics, it reminds you of physics for a reason. All of this terminology comes from physics. So conservative fields have some very nice properties that we'll discuss after we discuss the background for line integrals. But they have very, very nice properties. But here we're not going to get into those properties, not just yet. We're just going to determine whether a given field is conservative by trying to find the function little f, so the gradient of this function is equal to the vector function. I'll give you a test for those fields in R2 and R3, and then we'll talk about how to find this function little f. So let's say I've got a function f of x, y, excuse me, and that function is pretty simple. Just for example, let's just say that f of x, y, z, excuse me, is 6x times y times z. Well, if I take the gradient of this, that's going to generate a field. This would be the potential function for that vector field f. So let's compute the conservative vector field corresponding to this function. It's actually pretty simple. All you have to do is compute the gradient of this. Since this scalar function is a function of 3 variables, the gradient has 3 components. It's the partial of f with respect to x, with respect to y, and with respect to z. The derivative of this with respect to x, well, that's a constant times x if we're taking a partial derivative. The derivative of a constant times x is just the constant. The constant here is 6 times y times z. And then we'll take the partial of this with respect to y. That's a constant times y. The derivative of a constant times y is just the constant. The constant is 6 times x times z. And the derivative of this with respect to z, well, it's a constant times z. The derivative of a constant times z is the constant. Now, I know that those aren't constant in general, but whenever we're taking partial derivatives, we always assume that they're constant. Okay. So if somebody asked you to compute the vector field, the conservative vector field associated with a potential function, all you have to do is take its gradient. Now, most of the time, this problem is stated in the reverse order. Rather than giving you the potential function and asking you for the field, they usually give you the field and ask you for the potential function. Well, not all fields correspond to the gradient of some function. There are fields out there that aren't conservative, but this one happens to be conservative. This is the partial of this function with respect to x. This is the partial of this function with respect to y, and this is the partial of that function with respect to z. So there is a function f, it's this one, where if I take its gradient, I get this field. So this field is called conservative. Now, if you're wondering to yourself, how can I tell if I've got a field whether or not it's conservative? Well, we've got two tests. We've got one for fields in 2 dimensions, and we've got another test for fields in 3 dimensions. A very long time ago, I asked my students on a quiz, how do you determine whether a field is conservative? One student said, by its voting record. That's right. So funny. That's the comic relief for today. Let's see. Okay, so here's a field. Or actually, here's our test for conservative fields in R2. Excuse me. Suppose the component functions of f have continuous first partial derivatives on an open disk R. So we're in some region, little circular region in the xy plane, and the components of capital F have continuous first partials in that region. Then the field F is conservative if and only if the following is true. The partial of n with respect to x is equal to the partial of m with respect to y. And I think this really makes sense. So let's think about it. If f is conservative, well, then what do we know about it? Then f equals the gradient of some function little f, since this is a field in R2. So f has 2 components, m and n. This gradient has 2 components, the partial of f with respect to x and the partial of f with respect to y. If f is conservative, this is true for some function f. Well, the partial of this component with respect to y is that, and the partial of this component with respect to x is that. So if this is m, and I take the partial of that with respect to y, and this is n, and I take the partial of that with respect to x, if this is truly the gradient of some function little f, those 2 mixed partials should be equal. So that's what this is equivalent to. We're just saying the mixed partials of little f are equal to each other. If that's true, if the partial of this function with respect to y is equal to the partial of this function n with respect to x, then we're guaranteed that there's some function f of x, y out there that I can take the gradient of, and I can get that field back. So I think this is a common sense test. Notice that it is a test for fields in R2. You have a different test for fields in R3, which we'll talk about later. Okay, so let me give you a field and we'll determine if the field is conservative. And generally we like conservative fields just because they have some really nice properties that we get to take advantage of. Okay. So let's say f is the field 2 over y squared times e to the 2x over y times the vector y times I hat plus negative x times j hat. So I've got a field in R2. Now this is a scalar function. If you've got a scalar times a vector, you want to distribute that scalar. And I'm multiplying the original components that are right here by that. So I'm multiplying that one by y, and I'm multiplying this one by a -1 and an x. That's where that negative came from. It came from right there. And of course, we want to simplify. One of these y's will reduce with that y, and I guess we could write that as 2x over y squared if we wanted to. That might be even more helpful if I simplify it further. Rather than putting that y in the denominator, I think I want to bring it up to the numerator, and that's legal. I can, as long as I change that exponent from a +1 to a -1. And then here, I'll do the same thing. I'll bring the y squared up to the numerator, which means it's going to be a y to the -2. Okay, so if somebody asks me to determine if a field in R2 that has 2 components is conservative, the first thing I would do is simplify it. Then the next thing I do is identify m and n. M is your x component, n is your y component. And you're going to take the derivative of this with respect to the opposite variable. So this is the x component. I'm going to take its derivative with respect to y. And this is the y component. I'm going to take the derivative of it with respect to x. And again, that's because we're trying to confirm that the mixed partials of the function little f are equal. If the partial of this with respect to y is not equal to the partial of this with respect to x, then there's no function little f out there that satisfies this. So we just identify these guys, and now I just take the partials of each of these with respect to the appropriate variable. I'll do that on the next page. So we had 2y to the -1 e to the 2x over y. And then we had -2x y to the -2 times e to the 2x over y. And this is m, and this is n. So I want to take the partial of m with respect to y. Okay. And it actually might be helpful to rewrite that exponent, that y in the denominator can be brought up to the numerator as well. That is 2x times y to the -1 in the exponent. And when I write it like this, I see I have a function of y times a function of y, so I'll have to use the product rule when I take the derivative. That's my first function, and that's my second. So we'll take the derivative of the first and multiply by the second. And then we add the derivative of the second. Oops, 2x y to the -1. And then multiply by the first. Now this just requires the power rule. So we bring our 2 down. We bring our exponent down. 2 times -1 is -2. Multiply by y to the 1 less power. -1 minus 1 is -2. Okay, over here, I've got e to some power. And that power involves a y, but it's not just a y by itself, so I've got to use the chain rule. So first we do the derivative of the outside. The derivative of e to some power is e to that power. And then we multiply by the derivative of the inside by the chain rule. And bring that 2y to the -1 that's right there down as well. The derivative of the inside with respect to y is this constant, which is 2x. I bring it down, and then I use the power rule for the y to the -1. So I bring my negative down, multiply by y to the 1 less power. So that's my partial of m with respect to y. Let me simplify a little bit further. I've got a -2 and a +2, so that's going to be -4, and then an x. Y to the -2 times y to the -1 is y to the -3. So we're there. And then we can factor that exponential out. You could factor out a 2 and a y to the -2 as well if you wanted to, but I think I'll leave that part alone. Excuse me. All right, so we computed the partial of m with respect to y, and it looked like that. So take the derivative of the x component with respect to y. Now I need to take the derivative of the y component with respect to x, and we see if they're the same thing. If they're the same, the field is conservative. So we're computing the derivative, partial derivative of n with respect to x. And I've got -2x, y to the -2, that's right, e to the 2x, and that y to the -1, or it can be written that way by bringing that y from the denominator up to the numerator. Okay, so we're going to use a product rule. We've got a first function and a second function. According to the product rule, we get the derivative of the first. Times the second function undifferentiated, plus derivative of the second function, oops, put that in a slightly different order, but that's okay, multiplication's commutative, times the first. Okay, so now we just compute the derivatives of each of these pieces. Now this is a constant times x. The derivative of a constant times x is just the constant. The constant in this case is the -2y to the -2. And then this one involves a function of x inside an exponential function. Since it's inside, that means I have to use the chain rule. The derivative of a function, or of e to some power, is e to that power times the derivative of the inside by the chain rule. We've done this before, but now we're taking the derivative with respect to x, not y. And that factor, we just bring it down. Now this is a constant times x. The derivative of a constant times x is just the constant. Okay, so let's see what we have. We've got a -2 y to the -2 times the exponential. And over here, I've got a -4 x times y to the -3 times e to the 2x over y. And we can factor out that e to the 2x over y. Question is this derivative equal to this derivative? It is. It's exactly the same. So we computed the two partials, the partial of this, the x component with respect to y, and the partial of the y component with respect to x. Since they're equal, oops, that means the original field f is conservative. And remember what that means. That means there exists a function, and I'm going to show you some notation now for there exists. It's this little backwards e, this little shorthand that mathematicians and those of us that are studying math use to represent the existence of something. So there exists a function f such that the gradient of f is equal to the vector field f. All right, so that's our test for conservative fields in 2D. If the partial of the y component with respect to x is equal to the partial of the x component with respect to y, and the components have continuous first partials on some open disk, then this field is conservative. And I guess we didn't check the continuous first partials bit. Let's look at this. When we took the first partial of this with respect to y, we got this. We're going to have problems whenever y is equal to 0. But notice that the original function f is not defined at 0 anyway, so I think we're going to be okay there. As long as we're on a disk that does not contain y equals 0 on the interior or on its boundary, I think we're going to be fine. Well, actually, it doesn't matter if it happens in the boundary. We're just interested in an open disk. So that's telling us that this field is conservative. These two partials are equal to each other and the field is conservative on any open disk that doesn't contain y equals 0. And remember, y equals 0 on the x-axis. So it just has to be a disk that avoids the x-axis. Okay. Now, we just determined that the field was conservative. You might be saying to yourself, okay, that's great, but how can I find the potential function? Well, once we know the field is conservative, we can set up a system of equations to find a potential function. I'll show you how. So this is sort of a continuation of the last example. Given this vector field f, which we simplified to 2 times y to the negative 1 times e to the 2x y to the negative 1, and negative 2x y to the negative 2 times e to the 2x y to the negative 1, we know that this is conservative. Because the partial of m with respect to y equals the partial of n with respect to x. If someone asks you to find the potential function, well, all you have to do is remember what the potential function is. And that's going to give you a system of equations, and it'll allow us to recover this function, little f. So the fact that f is conservative implies that there is a function little f out there such that the gradient of little f is equal to capital F. Or equivalently, the gradient of little f, which is a function of two variables, x and y, is equal to this vector 2 y to the negative 1 e times 2x times y to the negative 1. And then over here, we've got negative 2 x times y to the negative 2 e times 2x y to the negative 1. Okay, so I'm just saying the gradient of little f is equal to this. Well, these two vectors are only equal if their components are equal. So we know that f is conservative, capital F is conservative, so that means this must be the partial of f with respect to x. That the x components must be equal. And this must be the partial of f with respect to y. So f is the partial of f with respect to x is equal to m, and the partial of f with respect to y is equal to n. That's in general. In this specific example, we'll have 2 times y to the negative 1 times the exponential, and then negative 2x y to the negative 2 times the same exponential. Okay, so if somebody asks you to find the potential function f, you're going to state this. Say there exists a function f such that the gradient of f equals this. Therefore, this vector equals this vector. Therefore, the partial of little f with respect to x must be the x component of the field. The partial of little f with respect to y must be the y component of the field. So you're going to do an existence statement. And that existence statement gets you here. Now remember, you're trying to find f. You're trying to find the scalar function f. You can take the gradient of to get this, to get these two components, excuse me. Well, we can do that. We can do that pretty easily. If I know the derivative of f with respect to x, if I want to get rid of that derivative, I just anti-differentiate with respect to x. So f of xy is the antiderivative of the derivative with respect to x, which in this case is m. So we're going to take the antiderivative of 2 times y to the negative 1 times e to the negative 2, or 2xy to the negative 1, with respect to x, treating y as a constant. Now remember when we started, or when we did this earlier this semester. What did we do? When we started the chapter on multiple integration, we did something like this. So now you see how it's useful. This is a partial antiderivative. This will recover f, but not completely, just partially. I'm going to take the antiderivative of this with respect to x. Now 2 times y to the negative 1 is constant with respect to x, so I bring that down. And now we'll need to use this rule. Remember this from Calculus 1? The antiderivative of e to the kx is the exponential. If I were using the chain rule to take the derivative, I'd have to multiply by k. Since I'm taking the antiderivative, I have to divide by k. That's what we have here. It just looks different because you've got all these variables. X is our variable, and as far as we're concerned, 2 and y to the negative 1 are constants. So the antiderivative of e to this power is e to that power, and then we have to divide by the constant part. Well, the constant part in this case is 2 times y to the negative 1. So we'll divide out the 2y to the negative 1. Now don't add c. We're going to add something that's constant with respect to x, but it may not be constant with respect to y. So I'll call it g of y. Those reduce, and we get f of xy is 2e to the 2x over y plus g of y, where g of y is some unknown function. So we haven't recovered f yet. We know it's this plus a function of y, but we need to identify that function of y. One way we can do that is we can do the same thing that we just did with the partial of f with respect to x, with the partial of f with respect to y. So I've got the function f of xy. If I've got its partial with respect to y, I can recover it partially by taking the antiderivative with respect to y, which happens to be n, that second component of our field. So we have negative 2x times y to the negative 2 times e to the 2x y to the negative 1. Oops, this should be a y. And we're integrating, or anti-differentiating, excuse me, with respect to y and treating x as a constant. Okay, now this looks pretty bad, but remember, x is just a constant. So I really have e to a constant times y to the negative 1, and then a constant times y to the negative 2 out here. This is a great candidate for u substitution. So we're going to let u equal the inside function. Now this is an integral with respect to y. So I need to take the partial derivative of this with respect to y, treating x as a constant. Ooh, I'm not even sure about the notation here. I'm going to put a little question mark because it feels a little bit wrong. So I'm taking the partial with respect to y of this. Like, that's not really du. That's okay. It's going to be the partial of this with respect to y times dy. I guess dy is this plus the partial of f of this with respect to x times dx, but we're assuming that x is held constant right now. So you have some function times dx. Dx is held constant, so this is 0. So it's gone. Okay, so now I can use equality. So this is equal to this. Derivative of this with respect to y is, well, there's a constant, bring it down. Derivative of y to the negative 1 is negative y to the negative 2. And actually, that's exactly what we have. So this is our du in the case that dx is 0, because x is being held constant. So we've got the integral of e to the u du, which is e to the u, plus a function that's constant with respect to y, but not necessarily with respect to x. So we'll say plus h of x, and then we back substitute. Okay. So f of xy is both of these functions. F of xy is this function and it's this function. Well, that tells me if this is f of xy and this is f of xy, then g of y, the part that's not the same on these two functions, and h of x, those two must be the same in order for this to be equal to this. But a function of y can't equal a function of x unless that function of y and that function of x are just constant functions. Like if these were both 7, that would be fine. We'd have this function plus 7 equals this function plus 7, and we'd be good to go. So I think that's what we're going to do. We'll just say that f of xy equals this plus this function, which happens to be k. So f of xy is e to the 2x over y plus k. That is our conservative, or that is the potential function for our conservative field. Okay. So we've got a definition of conservative fields. Conservative fields are just fields that are given by gradients of a scalar function f. The test for conservative fields in 2D is this test. If the partial of the x component with respect to y equals the partial of the y component with respect to x, the field's conservative. If not, it's not. And then I just showed you how to find the potential function for a conservative field. So we said, if the field's conservative, you have this existence statement, then you'll set the partial of f with respect to y, x equal to the x component of the field, the partial of f with respect to y equal to the y component of the field, and then you anti-differentiate. So you're computing the partial of f with respect to, for the antiderivative of the partial of f with respect to x with respect to x. That's going to give you f. And then you do it again. But instead, this time, you compute the antiderivative of the partial of f with respect to y with respect to y, and that also gives you f back, but partially. Then the last step is you have to compare these two functions. So I'm looking at this function and this function. Whatever they have in common, I can just write down. F of xy definitely has an e to the 2x over y term in it. And whatever seems different has to be the same. So if this g of y has to be this h of x, we need to figure out what that is. The only way a function of x could be equal to a function of y is if that function were a constant. So I put a plus k here. You could use plus c if you prefer, that's fine. But f of xy is this function plus k. And if you take the gradient of this, you're going to get this as its x component, the x component of the gradient, and this as the y component of the gradient. If you're not sure, you should check that out. Okay. So we anti-differentiated, and I didn't write down the last step. You have to compare the two functions. To find the potential function f of x, y. Whatever they have in common needs to be a part of it. Whatever that looks different needs to be matched somehow. So you're going to do some matching. And we said, since those depend on two different variables, they have to be equal to the same constant. Okay. Now the test for fields or conservative fields in 3D is a little different. Now we have to have some qualifiers. So let's say that F is a field with components M, N, and P. And M, N, and P have continuous first partials. And an open sphere Q. So we're basically looking at a solid sphere, what's inside, but not including that boundary. So here's Q. Q is the interior of the sphere. And while we're in the sphere, M, N, and P all have continuous first partials. If that's the case, then F is conservative if and only if the curl of F is the zero vector. And remember, we said that that's the same as saying that F is irrotational. So there's no point in the field that has a tendency, or where the field sort of has a tendency to rotate. I guess it really depends on what the application is, but we're thinking of F as the velocity field of a fluid. There's no point in the fluid where that has a tendency to rotate around some line. Okay. So let's look at a field and see a field and see if it's conservative. Now, generally, you're not going to be told which test to use. You have to infer from context whether you have a field in 2D or 3D and then use the appropriate test. Okay, so let's say this is our field. We've got y squared times z cubed times I hat, and then we've got 2xy times z cubed times j hat, and 3x y squared z squared times k hat. Question is it conservative? Well, first you notice that it's an R3. So then you'll compute the curl. If the curl happens to be 0, then it's conservative. If not, it's not. Okay. And you don't have to write it that way. I just like to write it that way because it reminds me that the curl is a vector. And if you don't remember curl of f, we can think of as the cross product of the del operator with f. So you put the components of the del operator in the second row. I hat, j hat, and k hat always go in the first row whenever you're doing any kind of cross product form. The second row includes the components of the del operator, and then the third row lists the components of the field. Oops, 3x y squared z squared. Okay. Just moving my camera over a little bit. I feel like I don't quite have enough space. So we would cross out the row and column containing I hat. Actually, I think I'll just write it out. I'll expand it this time. Just write down the I hat. And then we'll have the partial with respect to, whoops, y here, the partial with respect to z here. And we've got 2x, y, z cubed, and then 3x, y squared, z squared. And then we're subtracting j hat times. Cross out this row and this column. At the partial of f, or the partial with respect to x here, the partial with respect to z here, and I've got y squared z cubed and 3x y squared z squared. Then we're going to add k hat times, cross out this row and this column, then you've got this 2 by 2 determinant. Having trouble with my partial symbols tonight for some reason. Excuse me. Okay. So I think I'm going to just do the computation as I go rather than writing it out all at once. So I'm taking the partial with respect to y of this. Well, 3x is constant, z squared is constant, and the derivative of y squared is going to be a 2y. So do that, and then I'm subtracting the partial of this with respect to z. 2xy is constant, derivative of z cubed is 3z squared. And then we've got a -1 over here. Take the partial of this guy with respect to x. That's a constant times x. The derivative of a constant times x is just my constant. Then I take the derivative of this guy with respect to z. Y squared is constant with respect to z. The derivative of z cubed will be 3z squared. And then we take the derivative of this one with respect to x. It's a constant times x, so we just get that constant. And the derivative of this one with respect to y, z cubed is constant. Derivative of y squared with respect to y is 2y. And we simplify. Well, I've got 6xy times z squared here and 6xy times z squared there, so I get 0. And those are the same, so I get 0. And those are the same, so I get 0. So the curl of f is the 0 vector. So that means f is conservative. Now we could go and find we could go back and find the potential function for this one, but I would like to do one where whenever we match the constants, we don't just get a constant again. Those like g of y, h of x, all of that, what would have been a constant of integration but had to depend on a variable. I want to do an example for you that doesn't quite work out that way. So let's do one more example of finding the potential function. Now this time you're told to find the potential function of f. So that implies from context that the field must be conservative. So let's say we've got sine of y plus 1 over x. And x times cosine of y plus y cubed. Okay. We want to find the potential function. Okay, well, just like before, if this field is conservative, then this equals the gradient of some function f. So this must be the partial of f with respect to x, and this must be the partial of f with respect to y. So we've got our existence statement. So f equals this for some function f. And now we want to recover f from its partial derivatives. So we'll state that, well, that means the partial of f with respect to x must be m, which is sine of y plus 1 over x. And the partial of f with respect to y must be n, which happens to be x cosine of y plus y cubed. And if I've got the partial derivatives of f with respect to x and y, I can recover f partially by undoing those operations. So I'm going to undo this differentiation operation by taking an antiderivative with respect to the same variable. The antiderivative of the partial of f with respect to x will give me f back partially. Just undoing an operation. So our next step, whenever we're finding the potential function, is to compute that antiderivative. Well, with respect to x, sine of y is a constant. The antiderivative of sine of y with respect to x is that constant times x, and the antiderivative of 1 over x is natural log of the absolute value of x. And then we would add a constant of integration, but it has to be constant with respect to x, not necessarily with respect to y. So we'll have a g of y there. Okay? And then you need to compute the antiderivative of the partial of f with respect to y with respect to y. So x is a constant, I bring that down. The antiderivative of cosine of y with respect to y is sine of y. And the antiderivative of y cubed with respect to y, I add 1 to the exponent and divide by the new exponent. And then I need a constant of integration that's constant with respect to y, but not necessarily with respect to the other variable x. Okay, so both of these are the same function f. They just look a little different. When I took the antiderivative with respect to x and with respect to y, both of those recovered f partially. We have to put those two pieces together and figure out what f must be in order for all of this to be true. So this is f, and this is f. So whatever I see here that they have in common, I know that's part of f. So I see they have an x sine of y in common. So f of xy must have an x sine of y term. And then the parts that they don't have in common must be equal to each other, because this is really the same function. So it says natural log of the absolute value of x here plus g of y must equal this function of y plus this function of x. So I'm thinking h of x must be natural log of the absolute value of x, and g of y must be 1/4 y to the fourth. In order for these to be equal, this is the function of y that I'm looking for. This is the function of x that I'm looking for. Say almost. It's almost right. There has to be a constant of integration somewhere. So g of y must be this plus a constant, and h of x must be that plus the same constant. So f of xy has this in it. It also has a natural log of absolute value of x term. It also has a 1/4 y to the fourth term and a general constant of integration. So this is the potential function for f, that field that we started with. So you are basically writing down anything they have in common first, and then anything they don't have in common, make sure it matches up with something. So I've got a function of x here equals a function of x there, a function of y there equals a function of y there. So you can write down all of those unique pieces as long as there's something that matches it, as long as you can make it work. And then you should have a constant of integration. Now, if you have some piece that doesn't quite fit, that tells you that you must have made a mistake earlier. Or possibly the field that you started with wasn't even conservative, if you can't match these two antiderivatives. Okay, now we did not find a potential function for a field in 3D, but if f, which has components m, n, and p, is conservative, and you're trying to find little f, then you do this, you do the following. You're going to set f equal to the gradient of little f, which will have three components, partial with respect to x, y, and z, for some f. And we know that that's true because f is conservative. That's our existence statement. And that implies that the partial of f with respect to x must be m, the x component. The y component of the gradient must be the y component of the field, and the z component of the gradient must be the z component of the field. So have this, and you're trying to get the function little f of x, y, z back. So then you're going to compute three antiderivatives. So you'll compute f of x, y, z equals the antiderivative of the partial of f with respect to x with respect to x. And that's going to be some function of x, y, and z plus something that's constant with respect to x, but not necessarily with respect to y or z. So I'll have g of y, z here. And then you'll do the same thing with the partial of f with respect to y. You antidifferentiate with respect to y to recover f partially. And now your constant of integration can't depend on y, but it might depend on x or z, so you'll have that. And then lastly, you'll compute this one. I don't even know what letter. I'm like, should I use R? I know we use R for something else, but I'm just running out of letters here. The constant of integration can't depend on z, but it might depend on x or y. So you'll have all of this, and all three of these will be equal to f of x, y, and z. So you're going to look at these, you're going to say whatever they have in common, you're going to write that down. You don't need to write it 3 times. If these are equal, that x sine of y is definitely in there. Now, if anything occurs uniquely in each of these, make sure there's some function in the other versions of it that matches up with it. So if I've got a function of x here, I need a function of x in this one and the next one. If I've got a function of y here, I need a function of y in this one and the next one. Confirm that that works out, and then you'll write all of those unique pieces down. And if there's no constant of integration, or after you've done all of that, you should add a constant of integration. and that will give you your field. So I'm just going to leave you with that outline. You can practice that in the homework, and please let me know if you have any questions about that.